Welcome, January 12th LeetCode Challenge. Insert into binary search tree. You're given a root node of binary search tree and a value to be inserted into the tree. Return the root node of the binary search tree after the insertion. It's guaranteed that the new value does not exist in the original binary search tree. Notice that there may exist multiple valid ways for the insertion, so long as the tree remains a binary search tree after insertion. You can return any of them. So let's look at example 1. You're given the binary search tree as such called root, where the values are the following: 4, 2, 7, 1, 3. And the value to be inserted is value of 5. So in this example here, we insert it as n. So the approach was to insert the value as a leaf node at the end. Another acceptable tree, binary search tree, is to insert it at the front, the beginning. So this is now the first number of the binary search tree, which is 5, and the rest of the following is 2, 7, 1, 3, and 4. And that's how we go about inserting it. So we have two choices here: to insert at the beginning, or to insert at the end, or insert anywhere in between, in the middle if you wanted to. But so long as it is returning a binary search tree after the insertion. So some other examples here: we insert a value of 25 at the end as a leaf node, value of 5, and it's inserting onto one of the leaves here at the end. Alright, let's look at the constraints. The number of nodes of the trees, 0 to 10 to the 4, value of nodes between these two numbers. It's important to note that this is the important constraints. All the values of the node dot values are unique, so there's no duplicates. And the value is between these two numbers, and it's guaranteed the value does not exist in the original binary search tree. So any value that we add to the binary search tree is guaranteed that's unique, and it's guaranteed that it doesn't exist before. Alright, let's go about solving this. So there's a couple ways this is a binary search tree type of approach. You could do it iteratively, you could do it recursively, you could use depth first search, or use breadth first search, and any of those types of binary search tree manipulation. I'm gonna go with a recursive case. Let's just choose that, recursive case. And we're gonna decide where we want to add our value. I'm thinking that adding the value, let's make a statement saying that always add the value to be inserted as a leaf node at the end. So the new value to be added is a leaf node inserted into the binary search tree. So always ensure that's a leaf node. Bingo. So that's the approach we're gonna make, our assumption. Because I think it's a lot easier than adding it in the beginning, and then we have to like modify or percolate everything to make sure it fits the binary search tree criteria. Alright, in this kind of three conditions we want to take towards our approach. The first one is the root node given is null. So if that's the case, then we want to return a tree node, which is the class given above here, and we want to return the tree node with the value to be inserted and no children node, and that's about it. So if the root node is null, so if not root, return tree node and passing the value to be inserted. Alright, or the val, I should say. Alright, excellent. So we have the base case out of the way. So the next thing we want to do is do recursion. So how are we going to do this? So we need to know basically where to add the leaf node. So if it's a situation looks like this, we want to add it to basically the right node. But if there's an empty 3, it's empty here, we want to add it to the left side. So how do we know that? So let's take a look at the following. Let's see. So if the roots node value, I should say, roots value is less than the value to be inserted, then recurse to the right. Recurse the right to the right. And else, otherwise, that means that the root's value is greater than the value to be inserted. Then we are going to recurse, you guessed it, to the left. Alright, let's kind of model this out. So if the value is less than the root's value, root.val, then we are going to recurse to, oh wait a minute, if the value is, nope, this should be the other way around. Let's see, first to the right, that is correct. Let's just go to the bottom. Never mind, let's just move this around. Alright. So if the root's value is greater than the root value to be inserted, that's what's that saying here, then we want to recurse to the left. So we update root.left, and we call self function, which is calling insert into a binary search tree, BST, and we want to pass along the root.left and the value to be inserted. Alright, that's pretty much it for that. And then after that we want otherwise or else. We are going to recurse. That means otherwise that means that the value is less than the value to be inserted, then recurse to the right. So therefore we want to update root.right and call the self function recursively on insert into binary search tree. I'm passing in root.right and passing in the value. That's pretty much it. And then this, we want to return the root, because essentially we didn't change anything. We just insert the root, the value to the original root tree. Let's run this and see how it goes. Alright, that looks promising. Submit. Alright, there you go, accepted. So let's see. So this is a simple, basically recursive case, inserting into a binary search tree. Memory-wise, isn't very promising, it's very low. As time complexity and memory and space complexity are both kind of not very the highest there, but it works. Let's see. We do. So time complexity would be, I believe it's log n, because every time we iterate through, we just take the log of the value, the number of the nodes in the tree. Space complexity is the big O of the height of the tree, big O of h, where h is the height of the tree, the node tree, the binary search tree. And yeah, that's it. Have a great day, guys.